Okay. I'm going to talk about formally. I'm going to talk about stoichiometry today, um, and then with a subsequent dry lab next week, we'll reinforce what we're doing today. Okay. The word stoichiometry means the mathematical relationship between reactants and products. Now, usually when you talk about a stoichiometry problem, there's a chemical reaction that's happening. Up to this point, we've not had any to employ any chemical reaction calculations. We just basically rename what was, like how many grams of the 1.2 moles of water weigh? The water didn't change at all. It stayed the same. We were just renaming it. Today, we're going to talk about, well, what if the water changes? I'm going to deal with that. And that's where that balancing equation comes into play. Okay. Also, we have our 4 steps for doing all problems. That hasn't changed at all. Because remember, up to this point, I've been saying ignore number 1 because it's not a chemical reaction. Well, what if it is? You got to balance it. First thing, if you don't balance it correctly, 2, 3, and 4 are going to be wrong. So it's crucial, one, you know how to balance equations. And there are more worksheets on Canvas under files to practice. And then we're going to go through what's given, what are you trying to calculate, just like we did before, and then the setup. The setup is going to be longer, though, with stoichiometry problems. It's going to be one extra step involving the balanced equation. But it'll still be unit cancellation, just like before. No change at all. Okay. All right, this is what a typical stoichiometry problem looks like. "15 grams of water is formed. How many grams of methane are consumed?" In this problem, we're burning methane. So methane is the fuel. Oxygen is the oxidizer. And these are the products. So what the oxidizer does, it oxidizes each element. And that's how you get your product. So carbon oxidized is carbon dioxide. Hydrogen oxidized is water. Notice the products all have an oxygen part. Okay, so let's balance the equation. Let's see, it's going to be 2, 2. Okay. All right, so what's given in this problem? Yeah, 15 grams of water. It's just like before. Find the number. And I want you to put the H2O on top there. Excuse me. Yeah. All right. 15 grams of water. All right. Remember, yesterday I said the balanced equation does not give us a gram relationship. It gives us a molar relationship. So if we're starting with grams, we've got to convert to moles. And if you remember, that was grams. Now we're at grams of water. We want to know grams of methane. So the moles of water has to cancel. Notice how the water cancels. So it's just like our normal setups. Cancel everything except what you're trying to calculate. All right, that gives us moles of methane, but not grams of methane. So we've got to convert over to grams of methane. So methane is one carbon is 1201. Hydrogens are 1.01 apiece times 4. That means they're 404. So that's the molar mass for methane. One carbon, 4 hydrogens. So a mole is going to be in the bottom, which cancels. Gram on top. So the middle step is why we balance equations. We want to know that ratio between the coefficients in the balanced equation. Now, what if you didn't balance the equation right? This part would be wrong. And notice it's 1 over 1. Some of you are thinking, well, who cares if it's 1 over 1? 1 times anything is itself. The units won't cancel, though, if you don't put that step in. So regardless of whether it's 1 over 1, 2 over 2, you still got to put that step in there. Okay, and then you're just going to grind that sucker out. Okay, so 3 sig figs, 4 sig figs. How many sig figs is that middle one? The 1 over 1. I'm sorry, what? Infinite, because it's precise. That we're not we're not measuring. We just are calculating. I'm sorry?
Missing the 18.02 is missing that 2. Yeah. The second one, 18.02 grams.
Right. What about it?
If there's no 2 written down. It looks like 3 sig figs.
Is it? You mean right here? Is that what your question was? Okay. Yes. I should blame the meds I was on. Okay, so it's 13.4 grams of what? Methane. So this is a very simple gram to gram stoichiometry. We start with grams, end with grams. Now it's not going to get any more simpler than this. So this is the simplest stoichiometry problem. Now you can see why we spent a whole day on gram to mole conversions, a whole day on balancing equations, because here we're putting it all together. Now, there's one more elaboration we're going to do on this, and I'm not going to cover it today. It's when you have two givens. So it's crucial you understand how the one given works. Because when you're given with two givens, you have to multiply this process by 4. And each one is very similar to this. So if you don't know how to do this one, then you're going to have a cascading effect of not being able to get the right answer. And we call that limiting reactants. You can have 2, 3, or 4 givens. Doesn't matter how many. Now, this is where a chemical engineer comes into play. My first job out of graduate school was with Spreckels Sugar. And the funny thing, the Valley grows a ton of sugar beets. The way they process sugar, a white, pretty crystalline sugar, is they start with a muddy old sugar beet. So at the one end of the factory, they're crushing sugar beets and all that stuff. In the middle of the factory, they're crystallizing out the sucrose, the table sugar. And then they bag it at the far end, which is everything is super clean in the far end. You have to wear a clean jumpsuit designed specifically to not bring anything contaminants into the. But it starts off so crude. The beets are coming out of the trucks. They're they're muddy and everything. My job was to find out how to maximize the yield for sugar. So that means check for leaks. Is sugar water leaking out someplace? That's money. So I was performing a chemical engineering job. So chemical engineers typically optimize processes. I mean, 90% of the time, that's what they do. Now, another friend of mine was manager of a Union Carbide factory. And they produced all kinds of bad pesticides and there. Anyway, but his job was how many railroad cars full of, well, in this case, sugar beets versus how many tons of white sugar am I going to get out of here? And so his chemical engineers went through and optimized each step of the process. When we crystal out the sugar, is that optimized? Are there any leaks? When we're bagging the sugar, how clean a process is that? More leaks? So that was the name of the game for a chemical engineer. And that plant was located in Vacaville. You're probably too young to remember, but whenever you would drive through Vacaville, it would smell like garlic and onions, because that's what they processed in Vacaville. So I was on the job for like 6 months, and they said, "Oh, we're moving to Gilroy, another garlic haven." They were going to consolidate their 2 plants to 1 plant, and I didn't want to move to Gilroy, so I said, "Have a nice day." And but that was my first job, and it was funny when I interviewed for it. They had me go through the front end of the factory where all the mud is and everything, and I had on my interview suit, navy blue, white shirt, red tie, kind of like a politician's uniform. And everyone else was much more casually dressed. Some of them were actually dirty from the front end because it's muddy and everything. And here I was in this pristine suit. That was the last time when I worked for Spreckels that I ever wore a suit also. But it was funny. Well, anyway, it's like blah, blah, blah for good. Okay. Are there any questions about this setup? Okay. Let's practice this more. Now, the worksheet I'm going to give you for next week, your dry lab, has got a ton of practice problems. And I included the answers also. Yeah. It's Fridays from 11 to 2. in room 102, which is across from the horse skeleton. 102. And they usually have food in there. Yeah. Yeah. It used to be 10 to 2, but they changed it. So if you get here early, you can always go over there and just when you need to leave, just leave. Okay, let's look at another one. We're talking about, okay, this is the same equation now. We're going to burn methane again. So we need to start with a balanced equation. Okay, so balanced equation. What's given? Water vapor. Look for the number. Now we have gaseous water. Need to convert it to moles. What do we use for that? Remember that conversion factor? I wanted you to know there were three of them. One is Avogadro's number, other is a molar mass, and the other is gases. Yes, exactly. At STP. It's real important. That only is valid at standard temperature pressure. Okay, now we have moles of water. We need to put water on the bottom and methane on top. And that ratio is 1 to 2 from the balanced equation. Okay, now we have water cancels. We have moles of methane. We want to get we want liters of methane. So again, we're going to use a 22.4. Notice something here. If I multiply what's the answer? 1. Notice 22.4 is both in the numerator and the denominator, which means they cancel out. Now, you don't have to cancel out. You can just put it in your calculator, or you can cancel it out. Get the same answer. Now, even though I cancel out 22.4, the sig figs still apply. So if this would have been 2 sig figs, for example, you want to cancel it out, your answer would still be 2 sig figs. Okay, and all this is at STP. Now, some people learn by patterns. And did you notice a pattern here? The setup is exactly the same as the previous problem. So some people don't look at it that way. And they look at each problem individually. But as you do more and more of these stoichiometry problems, you're going to see a pattern emerging. 3 parts. 3 parts. You've got this part here. We're going from given to moles. This is the molar ratio. from the balanced equation. And then this is moles to calculate. Every single stoichiometry problem has got the three parts. Get it to moles. Once it's in moles, we can use the relationship from a balanced equation. Then we need to get it back to what we're trying to calculate. None of the problems I give you, I will want you to do. The answer is in moles. It'll always be something to something. Could be liters, grams, number of particles. Any of those. All those can go to moles. Then we can use our molar ratio from the balanced equation and then get it to what we're trying to calculate. Every single problem. Now, it could be that you may have an extra step on the very end. For example, on this one up here, I could have said how many kilograms of methane are formed. So that would, you put a conversion at the end to go from grams to kilograms. But as far as the basic fundamental setup is this one here. Now, when you do that dry lab next week on stoichiometry that I'm going to give you, I'm going to give you the answers as well. And the reason for that is, hopefully everyone will get 100 on that. But you'll notice when you're all done, you'll have the same setup every time. And by doing it a lot, it really cements you in. The next part, we're going to be working with solutions. And solutions have a very similar setup to this. They have a pattern. So some people like patterns, other people could give a rip. But the main thing is if you are that type person, once you identify the patterns. Okay. Now I'm using the same chemical reaction each time, but that won't be the case. Sometimes it'll be different reactions going on. All right, how many molecules of carbon dioxide are created if 34.5 liters of water are created? Okay, step one is balance the equation. Boom, we got that from the last problem. What's given? Okay, so 34.5 liters of water are created. How many molecules of carbon dioxide are needed to create that much water? First step, liters to moles. Next, we need to go from water to carbon dioxide. And now we have moles of carbon dioxide. Then we need to get the moles to number of molecules. That's Avogadro. Okay, so we have three sig figs, three infinites, three sig figs. Same setup. Liters to mole, mole ratio from the balanced equation, and then moles to number of molecules. Again, notice the pattern. It's exactly the same. Now, one thing you need to understand, and I've mentioned this before, I'm going to say it again. Certain things are always together. And there are 7 of them. So whenever I mention the word hydrogen, it's hydrogen gas. When I mention oxygen, it's oxygen gas. And frequently they won't put gas down. I try to, but it depends on your next class. They may not they just say hydrogen. Oh, hydrogen doesn't exist as H in nature, it's H2. The only way it exists in nature is just plain one H is if it's connected to something else. But by itself, it's H2. Oxygen by itself, O2, N2, and then all the halogens, fluorine, chlorine, bromine, and iodine. All those are also diatomic. Di meaning 2 atomic atoms. So for example, in this case here, if I left off the word gas, you need to go, oh, that's oxygen gas. Okay, so we're using the same old formula. It's right over here. So we're starting with 23 liters of oxygen gas. Now in this class, if I don't say STP, it is at STP, okay? If it's not at STP, then it's not going to be 23.4. It's going to be some other number. But under standard temperature and pressure, temperature is going to be, yeah.
Are you like show us how to like work through figuring out the different number like in the future?
Working out what it is, you mean? Yes, I'm going to show you called the ideal gas law. And that is used to convert between non-standard gas parameters. And it's a simple formula, but you grind it out. Now, in your next class, particularly 1A, you will not be working with standard 22.4 liters per mole. It's always going to be using that ideal gas law formula. At least with 2 people I know, 2 teachers of 1A. And it depends who you get in 2A or 3A. 3A is probably not going to be standard either. It's going to be something other than that. So what that means is the front end that's the ideal gas law. P is pressure, V is volume, N is moles, T is temperature. R is a constant. So instead of this cute calculation we do up here, you put the ideal gas law there instead, which we want as you put that in there. So you solve for moles. That's what it is. Because the first step is to get it to moles. So you put in your pressure, your volume, constant, and temperature. That would be this here. Okay, good question, but that's the way you do it. And it's a little more, the step is the same though. Get it to moles. If it's non-standard, you're going to use PV is equal to nRT to figure out what it is. Okay, that makes sense? Okay, so we got moles out here. We're trying to go to kilograms of carbon dioxide. Okay, so what's the next step? We need oxygen on the bottom, and we need carbon dioxide on the top. So we had 1 and 2 from the balanced equation. Okay, now we want to go to grams of carbon dioxide, and once we get to grams, we can convert to kilograms. So for carbon dioxide, it was it 18 or what was it? 1802, yeah. But we need to be in kilograms, not grams. Okay, so everything cancels. Except kilograms. And it's going to be 3 sig figs. Now, the basis of this is the same pattern we were running into. I just had to add on a last step to get it over to kilograms. Same setup though. Given to moles, mole ratio, moles, what we're trying to calculate every single time. Now, frequently when you do stoichiometry problems, they'll ask you for a yield, percent yield. So to do that, you need so it's theoretical yield, which is this here. So everything we've been doing up to this point is a theoretical yield. Life is not that way. You don't get a theoretical yield most of the time. You get something. So then you need to figure out, well, how well did the reaction go? You do that via a theoretical yield minus the actual yield over the theoretical all times 100. And it's the absolute value also. So what we're going to do is exchange the brackets to absolute value. And what that means is percent yield is always positive. Because if you don't have the absolute yield there, oh, we got a clock, by the way. Only took me 4 times complaining. So if the problem asks you to do a yield, then you need to know the actual mass of the product they got. Bring to the yield or the liters of whatever. Okay. Now in your labs, frequently they'll ask you for percent error or percent yield, and they always say 100%. And it's not 100%; it's 100. Because 100% is equal to 1. Okay. So say we got 4.64 grams of water produced here, and the actual yield was 2 grams. And I would ask you, what was the yield? So the theoretical is 464 minus 2 all over 464 times 100. That'll be your percent yield. I'm just showing you how to do percent yield. Some problems ask for, others don't. So, I'm sorry, what? Yeah. Well, what you're calculating is it's theoretical. Okay. So you need to have an actual. So all the calculations we've been doing so far, we're doing theoretical yield. If everything went perfectly, that's what you get. Now, being real, whenever you in organic, you always are faced with this problem because in organic chemistry, you're synthesizing stuff. And in all the labs, in my organic class, I asked them to do percent yield. So once they do the theoretical, then they weigh the product, and then that's the actual yield. Once they weigh it, then they can do this percent yield calculation. The problem with synthesizing something, like in another week or so, we're going to be synthesizing aspirin, and you're going to end up with a white powder. Problem with the white powder, it's polluted with leftover reactants and other things. So your job then is to then purify the aspirin by recrystallizing it, and then you weigh it. So there's always these problems of making your product you're trying to make purer. And that's why purer products cost more. It takes more labor and processes to get it. It's interesting when you're talking about this too. Food is not the highest purity level, which is stuff we eat. So the FDA says so many rodent hairs can be in the product, so many feces can be in the product. All those things are in the product. So what they do then is analyze their product, making sure that the minimum number of byproducts are not there. Everything is above food level. You know, here we're sitting eating away the old stuff. So the highest grade is analytical grade. It's usually about 50 to 100 times more expensive than a non-analytical grade. Real expensive stuff. Okay, so that's basically the beginning of stoichiometry. Now, after next week, after you do the dry lab, I'm going to show you the next step in stoichiometry, which is, this is an example of a more complicated stoichiometry. What's the given? There's two of them, right? So you have to do two calculations to figure out which produces less. Then you have to figure out how much of what you started with is consumed, left over. And then you typically do a percent yield. So there's 4 calculations there instead of 1. 4 calculations. See you next week. All right. Now we're not going to do this one today. Because unless you know how to do this here, you can't do the limiting reagent, limiting reactant. Okay. So we brought all those processes together. Balancing equations, unit conversions, and this is the simplest stoichiometry you're going to see. So it goes up from here. Okay? That's why I want you to really get into the dry lab next week. Okay, so that's what I wanted to cover today. It's simple stoichiometry. Now in lab today, you're going to be doing Lewis structures. And again, I want to repeat, only the Lewis structures on the lab. And don't do any sulfurs either. Sulfurs are an exception to the normal one. Yeah.
So are we just trending in like we trend in lab 1 and lab 2?
Yeah. Right. Yeah. So dry labs are not in your composition book. It's just a worksheet basically. So you're going to click on the assignment and it'll prompt you for a file. And that's going to be your scanned worksheet. Okay, so are there any questions about this? I've taken it in little bitty steps. In 1A, they don't. They go, blah, here you go, do it. So that's why Chem A is really an important class. Okay. All right, so that's going to do one other thing. I'm going to show you on Canvas. If you'd like to get started on next week's lab, these are all all the extra stuff. And the lab is going to be. I'll print it off and hand it out as well. So where is? This is it here. If you want to get started earlier, this will be it. Anyway, this is what I'm handing out for next week's lab. It's on under Unit 4 towards the bottom, almost the last file on the.
Well, are the labs.
Right, we're going to do this one instead. This follows up with the lecture.
The lab one is this week.
We're still going to do the nomenclature. We'll just do it later on.
Okay, sorry, can you repeat what you just said?
Yeah, we're doing the nomenclature lab later. And we're going to do my handout instead, so that it follows with the lecture. Yeah, and this is it here. Yeah, I'm gonna print it out for you as well. So if you want to print out your own and start, that's fine. One thing on this worksheet though, do problem 2 last. Yeah. The reason for that is the reaction's complicated. In fact, it's such a pain that I actually balance it for you. But I don't want you to spend a half an hour balancing it. That's not the focus of it. So you're gonna use these 5 problems relate to that reaction. These 2 relate to that. And you'll find these are very similar to what we did in lecture. Just different given a different time. Okay? All right.